we consider the region 0 less than or equal to x less than or equal to y, 0 less than or equal to y less than or equal to 2. It says that for every value of y between 0 and 2, we have the points with that value of y. Now let's just take this specific value here. Okay, there's a value of y, and this curve is the curve x equals square root of y. So x is equal to the square root of y on this curve. X is equal to 0 over here. For a given value of y, the value of y goes from, for a given value of y, the value of x goes from 0 to the square root of y. So 0 to the square root of y. For this y, which is a little bigger, the square root of this y will be a little bigger, we'll go from 0 to the square root of y. So we can think of traversing this region if we take every possible value of y and move from the y-axis where x equals 0 out to the curve where x equals square root of y. Here's a picture of the region. Now, this is part of the curve y equals x squared because, of course, we can square both sides of this. It's not the whole curve. The y equals x squared curve is over here, too. We could equally well describe this region. Let's first observe in terms of x going from 0 to the square root of 2 and y having limits that depend on x. If y is 2, then x equals square root of y, square root of 2 will be the limit, be the end of this segment, so that the maximum possible value of y being 2, the maximum possible value of x would be square root of 2. So this region is 0 less than or equal to x, less than or equal to square root of 2, but for every value of x, y goes from this curve up to this straight line. Now, what's the value of x on this curve? Well, the value of x is, what's the value of y on this curve above the point with the coordinate x? It's going to be x squared. So here, y is equal to x squared. Here, y is equal to 2. So y is going to go from x squared to 2. So we can express this region in either of these ways. Now, what if we want to find the area within this region, within this curve, or perhaps the volume underneath the graph of f of xy above this curve? If z is moving out at you this way, we have some curve up here, we want to find the volume that lies above this region. What we're going to do is we're going to think of partitioning the interval from 0 to 2 using this description, using y from 0 to 2. We're going to think of partitioning this interval, and then for every partition, every strip corresponding to the partition of this interval, from every yi minus 1 to yi, we have a strip running across here, and then we partition that strip with respect to x. X will go from something here to something over here. We're going to partition those values of x. So our partition from y equals 0 to 2 is just 0 equals y naught, which is less than, had a mistake in here. I changed the subscript here and didn't change the subscript here. This would be y naught less than y1, then less than y2, etc., up to yn, which equals 2. This should be familiar to you from your first year calculus. Where y sub I is going to stand for the endpoint of the ith interval of the partition. Now let's explain that. The first interval of the partition goes from y0 to y1. Okay, so y1 is the endpoint of the first partition. There are n intervals. From 0 to n, there are n plus 1 numbers. These numbers are like fence posts delineating the intervals. There's one more fence post than there is intervals, or fence sections. Okay, well, anyhow, this is the endpoint of your nth interval. This is the endpoint of the ith interval, where I is any index between 1 and n. In general, then, we're just going to take a typical strip or a typical interval of the y-axis here. There's yi minus 1, here's yi. Now, on this strip, our x values go essentially from 0 to the square root of y. But is it yi or is it yi minus 1? I'm not going to worry about that. I'm going to use yi. I'm going to partition the interval from the x interval from 0 to the square root of yi, and claim that that gives me some reasonable approximation that's going to lead us to technique for evaluating area and or volume. Okay, so there's the partition. Well, this is the interval that's being partitioned, and here's our partition. We're going to say that we're going to have m intervals in this partition. We don't want to have the same number in this partition we do in this one. We could, but we want to distinguish them. So I'm going to use m for the number of intervals in this partition. So my x values are going to go from x naught, which is the lower limit, 0, up to x sub m, which is the square root of y sub I. And the hesitation is that I wrote y sub j here. And that's kind of natural. You see me do it on the more extended videos. I'm always confusing this because it's opposite to the usual order that we use for the subscripts of y and x. Usually it's xi and yj, but the way I've got this set up, it's yi and xj. Okay, so there's a partition of this interval, and what this corresponds to, of course, these x naught through xm are just the values of x that delineate these little rectangles, so that a strip between yi minus 1 and yi is broken up into little rectangles by x naught through xm.